Finite difference time domain. This is the time domain brother to finite difference frequency domain. And if you followed everything with that method, this method follows, but I think is a little bit more complex in the formulation and implementation. The largest benefit in my mind of finite difference time domain over finite difference frequency domain is that it can handle nonlinear materials, transient fields, and much, much larger problems. It's argued that finite difference time domain scales linearly, meaning if you double the size of the problem, the number of computations only doubles. Whereas with finite difference frequency domain, when the problem size is doubled, the number of computations goes up 4 or 16 times or something like that, depending how you're solving it. So in finite difference frequency domain, we assembled a bunch of equations into a matrix equation, solved it with a backward division, and we had a snapshot of the fields at one frequency. Instead, we're going to solve Maxwell's equations in time, and this creates essentially a movie of the electromagnetic wave passing through your device, scattering, bouncing around, and you can watch that happen, and it iterates in time, and you can watch your fields evolve. It's a great tool for learning, great tool for visualization, great tool for doing really, really large scale problems. When everything else fails, finite difference time domain usually doesn't. So this is a relatively long lecture, and I did that to do a comprehensive summary of finite difference time domain, but even then I'm missing a lot of details. In fact, we have an entire semester-long course just on this method, and I am spending one lecture on that, just to give you an idea of how compressed this information is. But I can give you a pretty good feel of how FDTD works, how it's formulated, and even how it's implemented. And what you're going to see is a lot of commonalities with finite difference frequency domain in terms of how the fields are processed and analyzed, and the E-grid's also the same. So let's try to get a gut feel of what is happening with this method. We have 4 equations, essentially. We have the 2 curl equations, 2 Maxwell's curl equations, and we have our 2 constitutive relations. Now, let me describe this as a sequence of events, and technically that's not correct. All of these equations are simultaneously coupled. Everything happens at the same time, but in the framework of finite difference time domain, they absolutely work sequentially, and we can choose to start anywhere. Let's start in this upper left corner. What we'll do is we will calculate the curl of the electric field E. Based on the curl, we will know how quickly the B field is changing, so we'll know how to update it. We'll know what value to update, to add to the current values of B to update it, based on the curl of E. Once we have the new B field, we can use one of our constitutive relations then to solve for the new H field. Given the new H field, we can calculate the curl of the H field and update the D field based on the curl of H. Once we have the new D field, we can then go to our other constitutive relation and calculate the new E field. Given the new E field, we'll calculate its curl and we'll update the B field. Given B, we calculate H. Given H, we calculate D. Given D, we calculate E. Given E, we calculate B. And this is a time-stepping algorithm. And as this is happening, you can watch the fields move around, and it's a pretty neat method to watch. Now, very often we'll assume that our materials are linear, homogeneous, isotropic. We can substitute those constitutive relations into Maxwell's equations, and now we can understand Maxwell's equations in a slightly different context. We will calculate the curl of E, from which we can update H based on this proportionality constant, that is the permeability. Then given the new value of H, we calculate the curl of it and update the E field based on that curl with the constant of proportionality called the permittivity. So we can imagine this algorithm then, it bounces back and forth, calculate H, calculate E, calculate H, E, H, E, H, E, and it bounces back and forth, back and forth, back and forth. And at first, we'll initialize all the fields to 0, and we'll start the iteration. It's going back and forth, back and forth, back and forth, back and forth. But if the fields are all 0, nothing's happening. We're just going back and forth and calculating all zeros. So we're going back and forth, every point in the grid. Then at some point, maybe at the top side of your grid, as we're going back and forth, EH, we're going to start overwriting some of those values near the top of the grid in the shape of maybe a Gaussian pulse. So suddenly, as we're going back and forth, we introduce that first set of values. That set of values starts to move across the grid. We continue to inject this Gaussian type source, and we're going back and forth at each point of the grid, and we can watch that wave propagate across the grid. And if there are any devices, we can see the field wrap around that and do other crazy things. But it all comes from back and forth with Maxwell's curl equations. So that's the gut feel of how finite difference time domain is working. So the next is the details. We're very comfortable having worked through finite difference frequency domain, the staggering of the fields on the Yee grid, and we do that to satisfy the divergence equation. We also know that that satisfies boundary conditions, and it's also a very elegant arrangement for to approximate the curl operations. Well, it turns out we also need to stagger the field in time, so there's a whole other discussion for this time derivative. So we have this iteration between E and H. So clearly, we're going to need to approximate these equations with finite differences. We're very comfortable right now, hopefully, with approximating the curl by putting the fields on the E grid. Let's think about the time derivative. Remember that we want to use central finite differences. So let's take a look at this one first. If we use a finite difference that says E at a future time value minus E at the current time value over delta t, that calculates the time derivative of the electric field. But where does that exist in time? At t plus delta t over 2. So remember our rule, every term in a finite difference equation must exist at the same point, and that's in time and space. So if this term exists at the half time steps, then we're going to have to define the H fields to exist at the half time steps. So E and H are now staggered in time. The electric fields will exist at the integer time steps 0, 1, 2, 3, 4. The H fields will exist at the half time steps 0.5, 1.5, 2.5, 3.5. So when the H field exists at the half time steps, here's what we'll calculate its time derivative. H at t plus delta t over 2, where delta t is the duration of the time step, minus H of t minus delta t over 2. So the time span between these samples is delta t. So this term calculates the time derivative, and where does it exist? At the midpoint, which is exactly at H of t. And so since this time derivative, after we approximate it, exists at time t, that's when the electric field exists, which is consistent with what we talked about down here. So everything works out in terms of central finite differences if we stagger E and H in time. So from this, we're going to derive what we call update equations. So before we were talking about going back and forth. What that means is we have some kind of equation where we'll update the electric fields from the magnetic fields and then update the magnetic fields from the electric fields. So here's the basic way these are derived. We start with our finite difference approximation, and of course there's also finite differences approximating this curl, but we can ignore that for right now. And we have a finite difference equation that looks something like this, where we approximated these time derivatives with finite differences. So we have a field at a future time value and a field at a previous time value. And same thing for the electric fields. What the update equations are, we'll take these, which is a direct finite difference approximation from Maxwell's equations, and solve for the future time value, the field at the future time value. So we'll solve for this term. And when we do that, we end up with our update equation for H. Down here, our electric field, this is the electric field at the future time value. We'll solve this curl equation for that electric field, and now we have the electric field at the future time step is the electric field from the previous time step plus the curl of H multiplied by some constant, delta t over epsilon in this case. And the future value of H is the previous value of H minus the curl of E scaled by this constant delta T over the permeability in this case. So here's the anatomy that we talked through on the last slide. Our future time value is somehow based on a previous time value and the curl. And we'll call this the update coefficient. Notice these are constants. They don't change with time, so it makes sense that we would calculate this ahead of time. Now for just one little division, maybe that doesn't make a whole lot of sense, but once we start putting PMLs, perfectly matched layers, into this and other bells and whistles, those update coefficients get very big and ugly. But they're all constants of material properties and time steps that don't normally change with time. We can calculate that once before the main loop, and then we don't have to keep repeating that every iteration. That brings us to our next topic. Let's talk about the perfectly matched layer in the time domain. And this is really one of the most tedious parts of finite difference time domain. It's a very beautiful, elegant algorithm. However, this PML is a bit of a pain in the time domain. So for finite difference frequency domain, we introduced this uniaxial PML. So for consistency, we'll stick with that. But I will mention really state-of-the-art in finite difference time domain right now are what they call convolutional PMLs, which is really what we discussed as the stretch coordinate PML just in the time domain. And there's convolutions involved in that. And it's very efficient and works very well. We're going to do ours a little bit different in order to stay consistent with what we learned in finite difference frequency domain. So on this slide we have our basic PML tensor, and this should be no surprise to you from our previous lecture on PMLs. Just like before, we're going to come up with little fictitious conductivity terms. We'll set those to 0 in the problem space because we don't want to start absorbing energy here, but they'll go from 0 to 1, I'm sorry, 0 to something other than 0 out in these outer regions. And notice they're graded. We will start at 0 and go up to some other value, but we do this gradually. We don't just jump into having a conductivity there. We ease into it. So same thing as before. So in finite difference time domain, this method of calculating the PML terms works really well. We have our conductivity terms for x, y, and z axes, and we have this ratio again, x over the length of the PML. So x is the distance into the PML. That's the total length of the PML. So essentially this ratio goes from 0 to 1. 0 at the start of the PML and 1 at the very edge. We cube it to give it a profile that seems to work well, and we scale it. Once we have this fictitious conductivity, then we can calculate Sx, Sy, and Sz. And then plug it into Maxwell's equations. Now the perfectly matched layer really fundamentally is a frequency domain concept. So in fact, it's incorporated into Maxwell's equations in the frequency domain. Since we're formulating a time domain code, we then need to jump to the time domain, but now with the PML terms in here, and that's where things get ugly, because we have complex numbers that become integrations, and things get a little bit more involved. So up top here, we have 3 of Maxwell's equations. And what we did is we chose to write this constitutive relation separately. And here's why. We're ignoring the magnetic response of materials. If we didn't want to do that, we would have our second constitutive relation out here. But this is going to let us do something really neat. We can spend a lot of time on these 2 curl equations and get this code to work very fast, very efficient. Then over here in this much simpler equation, every possible thing we would want to do with materials is lumped into this one equation. So if we want to make the materials nonlinear, it's just this one equation. We won't have to touch any of the code that's messing with these curls. If we want something anisotropic, we can do it right here. We don't have to mess with any of the code over here. So it's a really good way to isolate doing tricky things with the materials so that we can spend time, get this code done, and we won't have to touch it again. Now there is still a permeability here, and like I mentioned, we could pull off and have a separate B equals mu H, but most of the time we tend to ignore the magnetic response of materials. There's plenty of interesting stuff when there is a permeability, but most of the time we ignore it in this. So this is called the EDH formulation, and this is what we'll proceed with. So let's stick the PML term in here, and as before, we stick S multiplying mu. We're not going to stick S in here. We could, and we could get that to work, but then that complicates this equation, and we want to keep this isolated and simple. So instead, we'll stick an S in here operating on D. Mathematically, this is absolutely possible, and this works just fine. Our next step is to normalize the fields. If you'll remember, E and H are 3 orders of magnitude different, and this can cause us numerical problems. Not all the time, but it's always good practice to normalize just in case we end up doing something where it would cause problems. Now, I always prefer to normalize the magnetic field because it's usually through the electric field quantity that we interact with our model. We give it the amplitude of our wave, we calculate other things, and if we've normalized the electric field, that's just one more chance of getting something wrong. It's one more step that we have to do. So I always prefer to normalize the magnetic field, but it seems to be convention to normalize the electric field when it comes to finite difference time domain. So to be consistent with that, we're normalizing the electric field. But it's the same concept. We're going to take the E, divide by the free space impedance. When we normalize the magnetic fields, we multiply by the free space impedance. Well, the D field, since we're using this, that's also an electric field quantity, and it is E over epsilon. And so it is normalized this way, a little bit different than the E field. So E and D are normalized a little bit differently. But we can plug our normalized parameters now back into Maxwell's equations. And this is what we're going to proceed with. And it shouldn't surprise you that our next step is to take our 3 equations that are vector equations and expand them into their component scalar equations. So now we have 9 equations. 3 from each of the curl equations, so that's a total of 6, and 3 from the constitutive relation. And also notice we are assuming diagonally anisotropic materials. We're retaining that because we have to incorporate the PML, which is a diagonally anisotropic material. And we know now if we want to account for fully anisotropic materials, we have additional terms and interpolations to do. So to simplify this lecture, we're ignoring that. We only have diagonally anisotropic materials. So we're going to expand our expressions for the Sx, Sy, and Sz, and we end up here, an alternate form. On the previous slide, we had the Sx, Sy, Sz. Now we expanded it in terms of the fictitious conductivity terms. So same equation on the previous slide, just a little bit different form. We eventually want to get the time domain version of Maxwell's equations. So there's some things that we can do to help us. One thing that's really going to simplify is to write down this curl term. So this is the curl of the electric field in the x direction. So it's the x component of the curl of the electric field. And that's what comes from this first of Maxwell's equations. This is the x component of the curl. So rather than keep writing this, we'll just write it as CEX. So now our equation becomes a little bit simpler. We don't have to keep manipulating these equations. We certainly could leave them in here, but I think it's a little bit simpler to write it this way. And it also helps us in terms of how we're going to implement this. We're going to calculate the curl and then update the field. Rather than have the curl in the update equation, we'll move it outside, and that'll also help us with our source when we get to that point. Okay, so if we look at the equation we had on the previous slide, one of the terms has an inverse. So what we'll do is we'll take this term and bring it over to the right-hand side of the equation. So here it sits. Now we can take this equation and multiply it out. And we end up with what we have on the bottom here. We're now at our final form of our frequency domain equation to convert to the time domain. And we do this one term at a time. So we have our first term, j omega h, And remember, j omega in the frequency domain is a time derivative in the time domain. So j omega becomes d dt. These sigmas over epsilon naught, that's just a constant in the frequency domain, so it looks exactly the same in the time domain. This next term we're dividing by j omega. If we multiply by j omega, like we did up here, it became a derivative. If we divide by j omega, it becomes a derivative in time. Next term, we just have a constant multiplying CEX, so that looks the same in the time domain. And then the last term, we had another j omega, which was another integration. One thing I'll point out is that notice these integrations are only non-zero inside the PMLs because we have these conductivity terms here, and there's another one. So outside of the PMLs, this integration is just always zero. So in fact, it's most numerically efficient to only perform these integrations in the PML regions rather than integrate everywhere. So here's a summary of where we are. We went term by term, and we converted all of these to the time domain. Here's our final time domain equation, and written all in black, here it is. Now, that was only for one of Maxwell's equations. If we go equation by equation and convert everything to the time domain, here's where we end up. So here's our 9 equations now in the time domain. We had 9 equations in the frequency domain. We converted to the time domain. But these are still analytical equations. Which brings us to our next step, is deriving our update equations from those time domain equations. So, we have up top our first analytical equation, and what we're going to do is go term by term and approximate this using finite differences, or in discrete time. So our first term, we have a time derivative. We know how to do that with a central finite difference. There's no time derivatives or anything here, so this becomes pretty easy to do. Now we have an integration. And in fact, this becomes a summation. Now you will notice that we pulled off a term here, and this is a longer story that we get into detail in the class. Suffice to say is, each term in this finite difference equation has to exist at the same point in time and space. But we're integrating up to t, which is an integer, not the half-time steps. And so that causes some problems because our h terms exist at the half-time steps. We have to do some kind of interpolation to get it to an integer time step, and that's the purpose of this. So don't worry about the whole lot now, just we're approximating an integral with a summation. Nothing magical happens to this term. That looks the same because there's no derivatives or integrals. And we have another integral now that becomes a summation. Now, there is not a problem here. We don't need this extra sort of interpolation term because we're integrating an electric field quantity which does exist at an integer time step. Here we had something that existed at half-time steps that we had to integrate to an integer time step, so there was a necessity for this extra interpolation. Suffice to say, there's a little bit more to that story that I'm glossing over, but you have the quick version of it. So now we have our time domain equation in discrete time form with everything approximated with finite differences. So if we do that for all 9 equations, here's where we end up. And there's a lot of algebra behind this, of course. So again, we'll grab the first one, and we are about to start deriving the updated, well, I guess we started deriving the updated equation, but we're nearing our last step. And notice what is in red here are the magnetic fields at the future time step. So in fact, we have 3 of them. And what this tells us is we have to multiply everything out, bring the future time step over to the left side of the equation, everything else over to the right, and collect coefficients, and solve for this term. So there's a bit of algebra left in that. When we do that, here's where we end up. Here's the update equation. Here's our H field at the future time step equals our H field from the previous time step times a big ugly update coefficient that I promised you we would get to, plus the curl of the E field times some big ugly update coefficient. But then we also have a summation term, an integration term, in fact two of them. One where we're integrating the curl of the electric field, and then the other where we're integrating the H field itself. And so we have four big ugly update coefficients. But notice everything in here does not normally change during the duration of a simulation. So this big ugly thing we can calculate ahead of time. And seeing those big ugly equations, I think, justifies why we calculate those ahead of time. There's a whole lot of math in that only needs to be done once. So in fact, here's how we actually implement it. Ahead of time, we calculate all of these update coefficients. So this is where all the coefficients collected into these terms. And we'll have 5 of them. We have an MHX0, an MHX1, MHX2, MHX3, and an MHX4. Now in fact, this MHX0 is not an update coefficient. It's just a big collection of terms that appears in all the other ones. So 1 divided by this times all this. So we really have 4 update coefficients, 1 through 4. But I like calculating this as a 0th update coefficient, if you will. And we do all of these ahead of time before the main loop. Then when we enter the main loop, we will be integrating the curl of the electric field by summing it. We will be integrating the H field by summing it. And we will be calculating the curl of the electric field. So given all these update coefficients are calculated ahead of time, given our 2 integrations and the curl term, now we can very quickly and succinctly update the magnetic field. The magnetic field at the future time step is the magnetic field of the previous time step times an update coefficient, plus the curl times an update coefficient, plus the integration of the curl times an update coefficient, plus the integration of the H field times an update coefficient. Now, we really have a unique update equation for every single point in the grid, because the PML terms can be different, the dielectric constant can be different, the permeability can be different. So in fact, these update coefficients are different throughout the entire grid. So we store these in an array, which is the same size as the array as our fields. And so we can get rid of all these other parameters once we calculate our update coefficients. We just retain a big array for this one, a big array for this one, a big array for this one, and a big array for that one. And we set up a loop, and we'll say, for nx from 1 to big NX, for ny from 1 to big NY, and for nz 1 to big NZ. We loop through our entire grid, and we run an update equation like this for every single point. So that's just the update equation for h sub x. Here is the update equation for h sub y. You'll notice that the final update equation has exactly the same form. It's just the update coefficients are a little bit different, and the curl term's different, and we're integrating slightly different quantities. But the form of it, its anatomy, is the same and does not change. Our update equation for h sub z, and our update equation for d sub x. Again, it looks exactly the same, even though now we're updating a d field. It's an electric field quantity, but its anatomy is unchanged. D sub y and d sub z. And I'll mention again, those 6 terms we update without any consideration of the permittivity. And that one simple little constitutive relation we've pulled out, which is the next slide, we've pulled that out so that any kind of crazy dielectric response we want to build in, we don't have to touch the update equations for those previous field components. It's all here in a much simpler framework. But just for ordinary LHI materials, we have 3 update coefficients that are just the reciprocals of the dielectric constants, and we update our electric fields from the d fields with these reciprocal of the dielectric constants. So a really, really easy step. And if you just have constant dielectrics that are isotropic, it may not even make a whole lot of sense to pull out that constitutive relation, but it makes a whole lot of sense when you're not sure what to do with that. You might want to modify your code to do anisotropic materials. You might want to modify it to do nonlinear or something else crazy. So I like to pull it out. Sometimes I'll even pull out the B equals mu h if something crazy is happening with the permeability. But anyway, that's the story of how the update equations are derived. Remember, we started with Maxwell's equations in the frequency domain form. We stuck in the PML terms. We rearranged things to make it easier for us to convert to the time domain. We converted to the time domain, but we still had an analytical equation. Then we approximated everything with finite differences or summations when there was integrations. Then we solved for the future time value, and all of these big ugly terms collected into these coefficients. We called our update coefficients, and last set of slides was summarizing all of the update coefficients for a fully three-dimensional FDTD algorithm. Now let's talk about how we inject the source, and I'll talk about the total field, scattered field source. There are other techniques, but I think this is consistent with what we did with finite difference frequency domain, and it is a really good way to implement a source. Just like in finite difference frequency domain, if we have something that is not periodic and we are not going to use periodic boundary conditions, so it's some finite sized gizmo that we're modeling, we have to have Dirichlet boundary conditions around all boundaries. We'll hit it with a plane wave, that plane wave scatters, we want to absorb it in the PML region so it doesn't reflect back in. And here's the basic grid scheme, and from our talk on finite difference frequency domain, this shouldn't be much of a surprise, but we'll have our device in the middle of the grid somewhere, whatever it is we're modeling. And if we're using periodic boundary conditions around the edges, really we're modeling a whole array of those little split ring resonators. But also remember from our other discussions, using the periodic boundary conditions really means we're only predicting the response in the middle region of this. The edge effects that might happen out here, we just can't capture with this type of model. But a lot of times we're only interested in what's happening in the middle, and this is a great way to do it. We're also going to divide our grid into the same two regions. In this case, we're going to have the total field region from this interface down, and our scattered field region from this interface up. Somewhere outside of the PML, but above the total field scattered field region, where we only are going to have reflected waves, we'll have a plane here where we record the reflected waves. We'll have a plane near the bottom where we're going to record our transmitted waves, and we still also want some space between our device and the PML. If there's any large evanescent fields sticking outside of this thing, we don't want those to touch the PML. Now there are some papers out there of how to design your PMLs to handle those evanescent fields a little bit better, but it's still always good practice to leave some space between your device and the PML. So here it's comparing the total field scattered field framework that we're talking about now for a fully three-dimensional model to what we talked about with the finite difference frequency domain. But the same concepts apply. We're really talking about the same thing here. And the derivation the derivation of the equation on how to implement this total field scatter field follows a very similar pattern. We know that we have finite difference equations at the boundary between the total field scatter field interface that reach across the interface. So on the scattered field side, there will be terms from the total field side that don't look like scattered field quantities, and that won't work. Likewise, we'll have finite difference equations on the total field side that contain scattered field quantities. Those aren't compatible. Those won't work. So we have to look at our update equations from that perspective and make those corrections. When we make those corrections, that's when our source appears. We'll have this one-way or a plane wave source coming in from the top to the bottom. So we'll have a plane just above and a plane just below that total field scatter field interface. And it's in those planes that we're doing our corrections. Remember how we isolated the curl equations, and here's one big reason why. The terms that reach across the interface are completely in the curl terms. So in fact, we can implement the source in the calculation of these curl terms and not have to worry about messing with the other big update equations that we just calculated. So on the scattered field side, we will be calculating the x component of the electric field. And what we'll notice, our z derivative, this will be the term that reaches across the interface. And in fact, this is our problem term. If we are just on the scattered field side, there's a k plus 1. This will be a total field quantity that we have to subtract the source from. And in fact, that's what this term is. This is subtracting the source from that term. We just brought it to the outside. Likewise, we also have the y component of the curl. And now here's the problem term. So our two problem terms, there's an EX and an EY problem term when it reached across the interface. And again, we're going to subtract the source term, and here's the subtraction. Now, the reason we brought these two terms outside the curl, what we notice is that we have our original curl expression here. So in fact, we can calculate the curl as we did before without considering anything about the total field scatter field source, and then just put in these corrections afterward. So that's pretty neat. Calculate the curl, not thinking anything about a source. Once those are done, then just in those two planes on either side of the total field scatter field interface, we introduce those corrections. And then those same curl terms then feed into our update equations, and there's no problem. So we've isolated where the problem we encounter when we're incorporating this. We isolated that work. Well, now we're on the total field side of the interface. We have terms now that reach to the scattered field that are not compatible. They don't work. We have to correct them. So when we calculate the x component of the curl of h, here's our problem term. We have an h sub y on the previous cell, which places this in the scattered field amongst a whole bunch of total field quantities. Well, we need to add the source to it. And when we do that, we add the source to it, we pull that term out, and here's the correction term where we added the source. Now down here, here's the problem term for the y component of the curl, the h sub x in the previous cell. So this is a scattered field quantity sitting amongst a bunch of total field quantities. We have to add the source to it, and we bring the correction out here. And again, we see that we have our original curl equations, which means we can calculate the curl just as normal throughout the entire grid, and then just in this plane, add these correction terms in. So let's think about the source terms and where they exist. When we modified the equations on the scattered field side, that required E field source terms. And in fact, those E field source terms existed on the total field side, as we're seeing here. Our update equations on the total field side reached to the scattered field side where we needed the source of the H fields. So in fact, we need to calculate the HX and HY components of the source on the scattered field side, and the EX and the EY components of the source on the total field side. Now remember, we're on a staggered grid. Those things are out of phase and also at different time steps, and we need to take all that into consideration. So let's start with the electric field. We'll just make the electric field a nice, ordinary, well-behaved plane wave. So here's our equation. It'll have a cosine. So we're actually injecting a pure frequency into this model, a pure cosine. And we have a polarization vector. Just like we talked about in finite difference frequency domain, that is the electric field component, the amplitude component of this wave. And we're going to make that so that the amplitude's 1. It's not necessary, but it makes our calculation of transmission and reflection easier. So remember, the two source terms that we needed were E sub x and E sub y. So in fact, here's our expressions then for E sub x and E sub y. And notice this is for normal incidence only. There's actually problems accounting for oblique incidence in finite difference time domain if you have periodic boundary conditions, and you also want to use a pulsed source. So most of the time, finite difference time domain just has a normal incident wave. If it's not periodic, or if any of those things are relaxed, we can get away with sending waves in at different angles. But there's our E sub x and E sub y source. Now we need to know what is the H source. And we want to be compatible with the E source. We have waves, E and H's are coupled. We need to make sure that this is right. So we go back to the curl equation. We have an expression for E source. We can plug it in here and then solve for H source. And in fact, here's what we get. So the H sub x has a negative sign with the y component of the electric field polarization vector scaled by the square root of epsilon over mu and times the same cosine. And then the H sub y has a px with the same epsilon over mu. And this epsilon mu are the permittivity, the relative permittivity and relative permeability where the source is being injected. And if we're talking about a plane wave source, that has to be a homogeneous region. So what if we didn't want a cosine source, we want a Gaussian source? Well, we have to generalize that a little bit, and we'll now define our electric field source. Instead of having a cosine here, it has the Gaussian profile. And when we put it in here, we have a Gaussian, but there's the time delay. We have the time delay because they're a half cell apart and a half time step apart. So that makes everything work for injecting a Gaussian. So what does the total field scatter field framework look like in 3 dimensions? I like using the slice command in MATLAB to visualize it. It's real easy. Maybe not the best, but it's definitely pretty simple. And what we see here is we probably had a total field scattered interface around here. It injected a pulse, and we can see the pulse traveling through the grid. And hopefully when it gets to the bottom and it reaches the PML, it gets absorbed and does not reflect. So that's a typical view of what you would see. And notice the amplitude's about 1, which is what we wanted. Okay, so we're at the point now where we've implemented the method, we have waves bouncing around, and we want to extract meaningful parameters. Well, very often we're interested in what the fields look like at a specific frequency, which are the steady state fields. So let's think about how to do that. We will go to our reflection plane or transmission plane, and we're going to record the field during the whole simulation. And if we excite it with a pulse, down the bottom here, here's our source. We excite with a pulse. So we have a pulse that heads toward our device. It hits this, some reflects, some transmits. And in fact, that pulse may bounce around a bit, but finally it leaves as either transmitted or reflected. So we inject the pulse, and what we see is, I'll look on the transmitted side first. We see our initial pulse, but clearly the pulse is bouncing around inside the device, and we see this as ringing. And we need to let the simulation run long enough that all of the energy has left the model. If it's very resonant, what you'll see is these ringings don't really decay that fast, and they might follow a slower profile like this, and we just need to let the model run and run and run and run until all the energy leaves. And on the reflected side, we would see something like this. So now we can Fourier transform these, and what we have is the steady state field as a function of frequency at this point and this point. So in one simulation, because we had a pulse which contains a bunch of frequencies, in one simulation we know the steady state field over a really broad range of frequencies. That's unique to finite difference time domain and a very cool aspect. If we're doing a very broadband simulation, a time domain method works really well. So this is brute force. And if we're interested in the steady state field everywhere, we probably don't want to store our grid at every single time step. We need something a little bit more efficient so we don't have to save all of that data each time step. So let's think of another way we can do this. We know we want to Fourier transform the field. That's what takes us from the time domain to our steady state fields. So here's the definition of a Fourier transform. Well, we're in discrete time, so we will approximate this integral with a summation. So take a look at this and reconcile in your mind that really is the same thing. Notice a couple of things. We can first of all take this delta t out of the summation. The second thing, we can look at this exponential, and all of these parameters are fixed except m. M is the iteration number. So every time step in our code, m will go 0, 1, 2, 3, 4, 5. And so what we can do is factor the m out of that. And we're going to call this the kernel. Exponentials are very slow to calculate, so we don't want to have to keep recalculating this for every frequency we're interested in. So we calculate this kernel once, and then every iteration where we're calculating a Fourier transform, we just raise it to the iteration number and multiply by the instantaneous field that we want to convert to the steady state. So every iteration, we raise this kernel to the power and multiply by the field we want to Fourier transform. And we add that to our previous tally, and we go through the entire simulation. And when that is done, then we might choose to finally multiply by the delta t. Not a big deal if we leave the delta t in here, and a lot of times I do that because I'm lazy, but for best numerical efficiency, we can do this after the main loop runs. But don't forget to do it, or your numbers won't make sense. So here's a summary of what I just said. We have the field at our current time step. We have this kernel raised to the time step integer. That thing will go 0, 1, 2, 3, 4 over the duration of the simulation. And so we just keep adding these up. We add to a tally over the whole simulation, and then in the end multiply by delta t. So every point where we are interested in Fourier transforming a field at frequency f, we will have another tally going. It's not one tally for a whole bunch of points, it's one tally per point. So if you want to calculate the steady state field in the entire cross section of the grid, we need to perform this Fourier transform for every point in that cross section. So if you have a 20 by 20 by 200 cell grid, the cross section would be 20 by 20, and we would need to be performing 400 integrations. 20 times 20 being 400. So here's the algorithm for the Fourier transforms. This is not the full algorithm for FDTD. We're just focusing on doing the Fourier transform. We will calculate a kernel that we'll call k sub I, not to be confused with a grading vector or anything. This is just k for kernel, which is our exponential without the m in there. We need one of these for every frequency that we're interested in. Not every point in the grid, just one for every frequency. So if we're simulating a device from, let's say, 1 megahertz to 1 to 10 megahertz in steps of 0.1 megahertz, we need 100 kernels because there's 100 frequency points. So we calculate all of our kernels ahead of time, one for every frequency. Then we initialize our Fourier transforms. Now we need one of these for every point in the grid that we're interested in Fourier transforming. Then we enter the main FDTD loop where you update H from E, update E from H, and we just talked through the DEH formulation where there's another step, but I simplified this to abbreviate the FDTD steps so that we could just look at the Fourier transform steps. But here's all your basic update equations, however you're doing it. And once you've finished updating, then for every point and every frequency that you're interested, we update our Fourier transform. So the previous tally, or that's the previous tally, plus the electric field that we want to Fourier transform at our updated time step, times the kernel, raised to the nth power, adds to the previous tally to give us our new tally. And then that will keep integrating over the duration. And then in the end, we can multiply by delta t. And as I mentioned, sometimes I'm lazy. If I don't want to do this last step, I'll stick a times delta t here and just take that little tiny hit in efficiency. Not a big deal. So remember this, the steady state field is calculated at a single frequency. And we need one kernel for every frequency that we're interested in. So if we calculated the steady state field at one frequency throughout the entire FDTD grid and looked at that, that should be the same answer that we would get had we performed finite difference frequency domain at that same frequency. So two ways to get to the same answer. A benefit of finite difference time domain, though, is in that duration of one simulation. We can actually Fourier transform at many frequencies and get the field over many frequencies from just one simulation. That's very unique. Okay, so we know how to implement FDTD, fields evolve, we can calculate steady state fields, Now let's talk about how to calculate transmission and reflection. And this really shouldn't be a big surprise having worked through finite difference frequency domain. So first of all, let's look at these Fourier transforms again. We had an initial source, a Gaussian source, and if we were to integrate that, what we would see is that the frequency content drops as we get to higher and higher frequencies. If we want energy out of these higher frequencies, we have to make this pulse shorter and shorter, which means our time steps will need to be smaller, which means we're going to need more iterations to run a simulation. So we don't want to make our pulse ridiculously small because that'll slow things down, but we want it short enough that the Fourier transform of that pulse encompasses all the frequencies that we're interested in. Another important aspect is this does roll off. It just doesn't have the same amount of energy at these higher frequencies, so there's some cutoff where we're not going to get accurate answers at these higher frequencies. So we record what gets reflected, what gets transmitted, and we Fourier transform those. Now notice we have that same roll-off behavior. This does not mean that there's less reflections happening at the higher frequencies. All that means is we just excited the device to begin with less energy up there. So clearly we need to somehow normalize our data and remove that artifact so we get the actual reflection and transmission as percents of applied power. So here's one last look at our Fourier transforms. We start with the pulse, that rolls off, and we see that same rolling behavior in the reflection and transmission, and that's what we want to remove. And we do that simply just by dividing our reflection spectrum here by the source spectrum, and dividing our transmission spectrum by the source spectrum. When we do that, we see that the reflection and transmission curves flatten out. So this actually is now reflectance versus transmittance. And we get reflectance by FFTing our fields and squaring it for power, and then also dividing by the source FFT squared, and doing the same thing on the transmission side. Then if we take these two curves and we add them together to look for conservation, we should see 100% conservation all the way across. Now FDTD, where we saw that transfer matrix method was almost perfect with conservation, down to 10 to the minus 15, 10 to the minus 16. Finite difference frequency domain was 0.1%. FDTD can be even less than that, and if you're within 1% of conservation, that's considered pretty good, in fact. So here's how we calculate the reflectance and transmittance. We go back to our grid scheme, and we have our reflection record plane, and we calculate EXREF and EYREF. So these are going to be FFTs that we've been calculating during the simulation, and in the end we have a steady state field EX and EY in the reflection plane, and then the same thing on the transmission plane. So we've calculated the steady state fields in the cross sections of the grid, one in the reflection record plane and one in the transmission record plane. Then we're eventually going to Fourier transform these to calculate amplitudes of spatial harmonics, just like in finite difference frequency domain. This is how we're going to calculate power. The first step in that is to calculate our wave vector components. And what we see is we have the X components, and there's an expansion of these because we have a grading if we're using periodic boundary conditions, and the same thing for the Y components. And so M and N are integers, and if we have let's say an 11-point grid in the X direction, M will go from -5 up to +5, passing through 0. So that's 11 numbers total. And this N is the index in the Y direction. So here's how we would calculate in MATLAB our wave vector expansion. So those are just the transverse components, and like always, these are continuous throughout the entire grid. Those don't change. It's the longitudinal component that changes, and we get those from the dispersion relations. So as before, here's how we're going to visualize our transverse wave vector expansion. We have a KX array, a KY array, but in fact together they're telling this one story. Here's what our wave vectors look like in the plane. And that is consistent throughout the whole grid. Those don't change. We calculate our longitudinal components from the dispersion relation, and we could potentially have different materials at the top and the bottom of the grid, so we calculate a different one depending whether at the reflection side or the transmission side. So those are the longitudinal components. We also understand that it's probably the only lower order few of them that's actually a real propagating wave. The others are evanescent and cut off, and in fact don't contribute to pulling power away from the device. So we ignore them. And here's our visualization of the longitudinal components and then the overall spatial harmonics on the reflected and transmitted sides. These also should not be a surprise to you if you're listening to previous lectures. Now we have another problem. EX and EY exist at physically different points. We can't readily combine them into a single electric field vector. We need to interpolate those to a common point. So we're interested in combining EX and EY. Let's interpolate both to be at the origin of the cell. And if we wanted the Z component, we'd do the same thing. We would interpolate it to be at the origin. So here's our equations for doing that. And we need to do this on the reflected side. So here's the reflected side X component, reflected side Y component, transmitted side X component, transmitted side Y component. So after doing that, we've interpolated our field components at the origin of the Yee cell. Now we can combine those in a meaningful way. So we're going to take those steady state fields, we've already Fourier transformed them, now we've interpolated to the origin, now we divide by the source spectrum so we get these flat reflection and transmission curves. Then we FFT those fields. We've interpolated them to a common point. We FFT them to get the amplitudes of our spatial harmonics. And we have the amplitude of the X component, amplitude of the Y component on the reflection and transmission side. So there's 4 different terms. And each of those are still the size of the cross section of the grid, how we're doing it. Well, we're missing the longitudinal components. So we go back to the divergence equation for that, and now we have an equation to calculate the longitudinal components along with the MATLAB code shown off to the right. Again, this shouldn't be any big surprise. And now we calculate diffraction efficiency using the exact same equations that we used before. And the reason we can use the same equations is we Fourier transform the fields. We're really doing calculations in the frequency domain now because we Fourier transformed them. So once we have all of the diffraction efficiencies, we can of course add all those up to get overall reflectance, add up all the diffraction efficiencies of the transmitted spatial harmonics to get overall transmittance, and it's always good practice to add those together and make sure that we have conservation of energy. Even if you want to include loss in your model or gain, turn that off at first, run your simulation, make sure you get conservation of energy, because if you don't, that's a sign something's wrong. Then you can turn your loss or gain back on. Anyway, I just took an entire semester course and lumped it into somewhere around an hour-and-a-half lecture. We are not going to implement this method in this class, although you could try it for a project. But there is a semester-long course on this, and if you haven't taken that, I would invite you to take it. It's a really neat method for visualizing fields and even learning electromagnetics. You can put in a device and actually watch the fields diffract and bend. Some of that behavior are frequency domain methods that we're concentrating on this semester. They remove you of that, and so they're missing that information, and FDTD would provide that.